All right, so I'm just going to run through some of the kind of theory and definitions you need to know from the number systems chapter in your book. So there are a few different sets of numbers that we need to know, some of which we may have encountered before and are kind of happy enough and familiar with. Others might be newer to us. So they are natural numbers, integers, rational, irrational, and real numbers. And I'll go through these in turn now. Natural numbers we should be quite familiar with. So they are the positive whole numbers. They're referred to sometimes as the counting numbers. They're the first set of numbers that you'll learn when you're growing up. So 1, 2, 3, 4, 5, 6, etc. Okay. The symbol for natural numbers is an N with just a double line on the diagonal. You need to be able to put all these on a number line. So if I want to put natural numbers on a number line, I put a dot on 1, 2, 3, 4, 5, and any positive whole numbers that I've got on my number line. So it doesn't include 0, doesn't include any negative numbers, doesn't include any kind of fractions or decimals in between the whole numbers. So you just put dots on the positive whole numbers, and that is the natural numbers graphed on a number line. Next up is integers. This is whole numbers again, but it includes negative numbers and it includes 0. Okay, so 0, not a natural number, but is an integer. The symbol for integers is Z with a double line on the diagonal again. So integers -3, -2, 0, 1, 2, 3, all the way up to all the whole numbers to positive infinity, all the whole numbers to negative infinity then as well. If I wanted to put it on this number line, so I would put dots on all the whole numbers. Okay, so all the positive ones, as I had before on natural numbers, but then 0 as well, and -1 and -2 and -3, etc. Okay, but not filling out anything in between the whole numbers yet. Okay, so integers is still just whole numbers, so just dots on the actual numbers. Next up is rational numbers. So these are numbers that can be written as a fraction, okay, or as a ratio. Okay, so we say in maths in the form P over Q, and I'll just return and tighten up that definition later, but just it means we can write it as some number over some other number. So P and Q there are just whole numbers. So you can write it as a number over a number. You can write it as a fraction. That makes it a rational number. Okay. So examples: 1 over 3, number over a number. All natural numbers and integers are also rational numbers. Okay, so 4 is a natural number. You can write it as 4 over 1, so that means it's a rational number as well. Say -5 is an integer. You could write it as -5 over 1. You've made it a rational number now as well. So all the natural numbers are also integers. All the natural numbers and integers are also rational numbers because you can write all of them over 1. -3 over 2, that's a rational number that wouldn't have been included in the set of integers because it's -1.5. Okay, so it's not a whole number. 15 over 2 or 7.5, that's a rational number. You can write it as a fraction, but wouldn't have been included in natural numbers because it's not a whole number. Okay, the symbol for rational numbers is the letter Q. And we usually just put a double or kind of a line there, a vertical line just on the left-hand side of the letter. The flip side of rational numbers is irrational numbers. And irrational numbers are numbers that cannot be written as fractions. So we cannot write them in the form P over Q. All right. The classic examples to remember are pi and √2 and √3 and √5 and all the surds. Okay, E is as well. That's another kind of constant like pi that you'll encounter at leaving cert. In decimal form, these numbers go on forever without occurring. Okay, so pi goes on forever without any pattern or without any repetition in the numbers after the decimal. There's no pattern or there that repeats. √2 is the same, √3 is the same, all the surds are the same. Okay, not all square roots are irrational numbers. Okay, so I have a kind of test if something is rational or irrational on the next slide. So if you put it into your calculator and press change or SD, depending on what type of calculator you're on. If the calculator gives you a fraction or a whole number, you're dealing with a rational number. If it doesn't, if it won't give it to you as a whole number or as a fraction, you are dealing with an irrational number. So just to show that, so let's say the square root of 16, that's equal to 4. That's a whole number, okay? So the square root of 16 is not an irrational number, okay? It's equal to 4, which is 4 over 1. That's rational. If I was to put in the square root of 5 and press equals, I get the square root of 5. I press change, I get all these decimals, I press change again. So I never get it as a whole number or as a fraction. So that means the square root of 5 is irrational. You cannot write it as a fraction. Okay, so the calculator can only show you this many decimals, but those decimal points, those numbers after the decimal point will go on forever without any sort of pattern. All right, so that's irrational numbers. All the numbers then that we have looked at so far, so natural, integers, rational, irrational, are real numbers. Okay, so real numbers is the set of all numbers. All right. So it includes rational and irrational numbers. So everything we've looked at so far is a subset of real numbers. So real numbers includes all the whole numbers and includes all the rational numbers. So includes all the kind of fractions in between the whole numbers. So if you're putting it on a number line, you would shade it in like that. Okay, so I don't just put dots on the whole numbers now. I actually shade in the entire number line because, say, between 2 and 3, there's infinite number of kind of decimals and fractions that you can get between 2 and 3. So I shade in everything between 2 and 3. Okay, and everything between all the whole numbers. Okay, so that's to show that real numbers includes all numbers, including fractions and decimals. So I'm shading over the entire line. Okay, there's just an example of some of the infinite number of real numbers that there are. Just to return to irrational numbers for a second, so they are like pi and square root of 2 and square root of 3 and square root of 5. They do have their own symbol, but it's not used on our course. We generally refer to them using symbols we already have. So irrational numbers, they are real numbers, but by definition, they are not rational numbers. So the symbol we use is just real, not rational. So or is real numbers. This symbol here means not, and Q is rational numbers. So real, not rational. That's the irrational numbers. I think I forgot to mention that in the last slide. So the symbol for real numbers is or, and you do just a double line on the vertical there. All right. This diagram comes up from time to time in questions. You'll see it in your book a couple of times. So it's just showing you that all those sets of numbers are nested within each other. Okay. So this smallest circle here in the middle, that's the set of natural numbers. So that's just the positive whole numbers. Z then, so this circle here is integers, so it's positive and negative whole numbers. Okay, so the positive whole numbers are a subset of the positive and negative whole numbers, so it's inside it. Q here, so rational numbers is this circle, so it includes fractions. All right. But because you can write any whole number as something over 1, the two of these circles go inside the rational circle. All right. All the numbers then that we've looked at so far are real numbers. So that's the kind of outside circle I've got in this diagram. And the numbers which are real but not rational going outside in this bit of the diagram are the irrational numbers. Okay, so real, not rational. So pi and root 2, etc. So you can be asked to put numbers on that diagram. So let's just say, picking some examples that aren't there. If I was asked to put the number 4 on that diagram, it would go right in the center. It's a positive whole number. If I was asked to put the number -7 on that diagram, I would put it here. It's an integer. Okay, so put it here. If I was asked to put 3 over 5 on that diagram. That's a rational number, so I would put it here. If I was asked to put minus 3/4 in that diagram, it would also go in this section. It's a rational number, okay? So that's where it goes. So you put it in, I suppose, the smallest circle it fits in. If I was asked to put the square root of 7 on that, I might just check it quickly. Is the square root of 7 rational or irrational? So square root of 7 equals that. And change. So it won't write as a whole number or as a fraction. So it must be an irrational number. Okay. So it would go out here. Okay. You see then that even not just pi in its own, but say pi over 2 or anything with pi or anything with an irrational number in it should go out here in the irrational section. All right, so you can be asked to put stuff on a diagram like that. Another example testing this is this one here, where you're asked to just tick what sets these numbers belong to. So you can pause this and read through that if you want. I'm just going to run through it really quickly here. So root 5, is that a natural number? No. Okay, we've seen already root 5 is a surd. It's going to be an irrational number. So I would say no to natural numbers. I would say no to integers. It's an irrational number, so that means it cannot be written as a fraction. It is not a rational number, so it will be no to this, yes. Okay, so this is irrational, and then it would still be yes to real. So all the numbers we look at in our course are real numbers. Positive 8, that's a natural number. It's a positive whole number, so yes to this. It means it's also an integer, so yes to this. I could write it as 8 over 1, so it is a rational number, so it will be yes to this. Is it irrational? No. Okay, so you cannot be rational and irrational. So if you yes for one of these, it should be no in the other box. So yes here, no here. It is still a real number, so yes over here. Minus 4 is negative, so it will be no to natural numbers. It's a whole number, negative whole number, so it will be yes to integers. You can write it as minus 4 over 1, so it will be a yes to rational. If it's a yes to rational, it's a no to irrational. Still a yes to real, so everything we're seeing are real numbers. 3.5, you could rewrite that if you want as 7 over 2. So if you put that into the calculator, it will tell you it's 7 over 2 if you're not too comfortable doing that. Not a whole number, so no to natural. Not a whole number, so no to integer. It's 7 over 2, so you can write it as a fraction, so that will be yes to rational, and then no to irrational. Okay. Yes to real numbers. Okay, so everything we're looking at is going to be a real number. 3 pi over 4, so it's got pi in it. So that is telling me it's irrational. Once you see that symbol for pi, it's irrational. It's not a whole number. It's not natural. No, not an integer, not rational. Okay, so once pi is there, it's not a rational number. I know it looks like it's a fraction, but once pi is there, it's irrational. So yes to irrational, no to rational. Still yes to real. It is still a real number. In the case of root 5, explain your choice in relation to the set of irrational numbers. I said root 5 was irrational. So that's because root 5 is a surd. It cannot be written in the form P over Q. It cannot be written as a fraction, so it is an irrational number. All right. You can pause on that just to go through that table if you like, and then just a couple of short things to finish off. So first one, division involving 0. So just as a section of the book on this, 0 divided by any number is 0. So if 0 is on top of your fraction, the answer is 0. So 0 divided by 2 is 0, 0 divided by 30 is equal to 0, 0 divided by 4 million is 0. On the other hand, though, dividing by 0 is undefined. Okay, so there's no answer. We cannot divide by 0. So 2 divided by 0 is undefined. 30 divided by 0 is undefined. If you put it in your calculator, you will get error. Because of this second point, because you cannot divide by 0, you cannot write a fraction with 0 on the bottom. The strict definition of a rational number is one that can be written in the form P over Q, so it can be written as a fraction. P and Q are integers, so P and Q are elements of their whole numbers, but Q is not equal to 0. So Q, the number on the bottom, cannot be 0. Okay, so that's just a little point on division by 0, and it kind of gives us this little bit at the end of our definition of rational numbers. And then just final thing I want to say is you will find a summary of these on page 23 of the log table. So you should know them, but if you were to have a blank on the day of an exam, page 23 will give you a little kind of